Okay, so the final project is up, and it's basically you have to write a Navier-Stokes solver from scratch. Right? And you know, we've been looking at each individual component of the solver up until now. We've looked at how to do the diffusion part, how to do the pressure, solving the Poisson's equation, and how to do the advection. Okay, and it's just combining everything together. Sounds simple, but it took me about 6 hours to go from scratch to end, right? Because you always have to do a lot of bookkeeping, there's bugs. So again, please start early and come to me anytime if you need help. So there's two problems mainly. First is you have used this velocity field before for doing 2D advection. So it's the same, spinning vortex. It's called the Taylor-Green vortex. And now you have to start with that as an initial condition. But then it will decay because of viscosity. So slowly you will see the velocity values will go down. Okay, and there's actually an analytical solution to this. So if you know the viscous coefficient, you can analytically, you have the exact answer. So when you write your solver, you can compare it to this exact answer. All right, and the next problem is something more, let's see, more along the lines of what you need to do when you do real simulations. In real simulations, there's always walls and there's objects, and you have to figure out what flow around them looks like. So here it's a simple case where you will put in two walls, parallel flat plates, and there's an inflow, and you will see how the velocity develops. So just in case it's not clear from the wording in the document, this is what the case would look like. So you have domain, and you put in two walls. The thickness and the length are known, right? And they're centered at the channel, and there's inflow. Okay, and the initial inflow is given to you, and you have to figure out what happens over time. And you can use periodic boundary conditions in all directions, in X and in Y, just to keep it simple. All right? And how do you account for this wall? You can do that using the penalty term. We looked at that a few lectures ago, where you basically force the velocity to be the velocity of the solid, right? And then, yeah, there's instructions around the simulations and create videos. All right, so all of this is due at the end of the term. I believe it's April 22nd, but again, don't leave it for the last minute. Okay, any questions about the project? This is 30 points, that's 30% of your total grade. Okay, so there's also the extra credit assignment. You don't have to do this, but if you feel like, if you're curious about the problem or you feel like you need some extra points for your grade, please go ahead and give this a shot. For this assignment only, you cannot collaborate with other students, okay? Everything has to be done individually without any sort of collaboration. Okay, let's see. So the task here is you will, in the project, it was a simple wall, right? But now you can pick any object that you want, any irregular shaped object. Okay, you can, for instance, you can have the word CTEC moving around in a domain, right? And visualize what the vorticity looks like. But the only condition is this is no longer an inflow thing. So you don't just sit there and watch what happens when a flow comes by. There's no constant flow. Basically, think of what happens if we have the tank, the water testing tank outside, and you drag around an irregular shaped object. So what would the flow look like? So that's the idea. So you take your object and you move it around, and then compute the flow using. And again, with using penalty, you can do this very easily because U solid just becomes what you want to impose. Okay. All right. And also with the videos you make here, try to be, try to make it nice and engaging. For all the projects, it's, the main focus is on doing things well and doing things correctly. But here, be creative. That's the idea. If you have any interesting projects that you want to do, not what's written here, again, you're welcome to contact me and we can discuss, set the scope of that. Okay, but the only condition is you will have to code from scratch, no using established solvers like Fluent or something. So that's it. Any questions? All right. That's also due at the end of the term. Okay, so today, all right. So today I want to finish up with just a few leftovers from spectral methods, and then we'll start talking about finite volume methods. So let's see, we were talking about the Fourier spectral methods. Where the momentum equation looks as del u kappa, del u hat of kappa plus the Fourier transform of u del u by del x equal minus I kappa over rho p hat minus k squared mu u hat. Right? And we talked about how this term needs to be evaluated in real space because in Fourier space this would be a convolution, which is very expensive. Okay? And the advantage of using Fourier methods is all our space derivatives have disappeared. dp by dx becomes p hat. d2u by dx squared becomes k squared u hat. Just this nonlinear term is the main issue. So that's the first advantage, right? So there's several advantages. Okay, we basically we have to deal with algebraic equations. Now, instead of differential equations. Yeah. Okay, so that's something that makes our life simpler. What is another advantage? Think about what happens when you compute this u hat. How do you compute the u hat? Basically, okay, I might have you taken FFT, but if you think about what's happening, it's an integral going from x equals minus infinity to plus infinity, or in our case, x equals 0 to 2 pi, because the domain is periodic. So you're basically reconstructing the signal u hat by using information at all available grid points. Okay. If you think about finite difference, what do we do? If you want to compute derivative at a certain point, you look to the right, you look to the left. and that's all you have to work with. But now in Fourier space, you have this I, K, U hat, and U hat has been computed from using all points. So does it make sense that this would be a more accurate representation? It does, right? And that's actually a very big advantage. Spectral methods have exponential convergence. What does this mean? It means that, let's see, if we have a first order finite difference, the error drops as order delta x. All right. We have second order finite difference, error drops as order delta x squared. Okay, but the error for spectral schemes drops much faster with increasing grid resolution. Okay, why do you think that is an advantage? The error drops much faster with increasing grid resolution. So how does that help us? Go ahead, take a guess.
A lot less error?
A lot less error, and if you decide my error that I can work with should be 1e minus 8. What would the difference be with a finite difference scheme versus a spectral scheme? Do you know what I mean? So
you could use a coarser grid?
Yeah, you can use a much coarser grid if you go with spectral methods, okay, and get the same accuracy. And that's a huge advantage in terms of saving computation time, saving RAM, memory. But everything comes at a price. So we will see what are the disadvantages. So this means we can conduct very accurate simulations using a few grid points. And again, this is relative. It's in comparison to finite difference scheme. Comparison to And for this reason, these methods, the spectral methods, are the method of choice when people study turbulence. Okay. I will discuss turbulence in some detail over the last two classes, but if you remember, turbulence involves a large separation of scales. Things might be happening at very large scales, but energy eventually gets dissipated, destroyed at very small scales. So if the simulation does not resolve these very small scales, we won't be able to reproduce what's happening physically in the flow. All right. So for this reason, spectral methods are preferred Okay, and I have to add here of simple turbulent flows. All right, so it seems like, all right, these spectral methods are very nice. They simplify our differential equations quite a bit, and they are very, very accurate. So, but what's the drawbacks? What's the disadvantages? So if we talk about disadvantages, and there are several, okay? All right, do you know many? Think in terms of the Fourier transform. What is one assumption we have made in the Fourier transform? You know, the analytical Fourier transform requires integral from minus infinity to plus infinity, or if you are periodic, from 0 to 2 pi. So what's an assumption in there?
That we're assuming it's periodic?
Yeah, we're assuming the domain is periodic. Otherwise, we have to go from minus infinity to plus infinity. Doesn't make sense, right? So that's why I wrote simple. The very simplest homogeneous turbulent flow is called homogeneous isotropic turbulence. It's a very simplified representation of what happens in turbulence. Okay. So there, you take periodic boundary conditions in all three directions, but that never happens in reality. Right? There's always a wall. Periodicity doesn't make sense with walls. Okay, so there are ways to work around this. For instance, you can use the cosine transform, but again, you have to take care of these things, right? So the first disadvantage is let's see, requires periodic boundary conditions or very simple boundary walls, let's say. So if you have a flat plate, it's relatively easy to do this using spectral methods. But if it starts getting complicated, it becomes a nightmare. All right. Another thing is, if you remember some of the simulations we saw, the grid cells were not uniform. Right? You put down more small-sized cells in regions where things are happening, and you take away cells from regions where things are not happening. Right. So that's that were basically non-uniform grid cells. Okay. So you cannot have such unstructured meshes. So FFTs cannot be used in simulations. With adaptive or unstructured meshes. Okay, and more disadvantages is, let's see, if you have an irregular shaped object, a potato inside, how do we impose boundary conditions over here? Okay, so it's very difficult to simulate flow around complex shaped objects. All right. In terms of computing, it scales relatively okay until you get into very large problems. So in parallel computing, scaling means, if I throw 4 times as many computers at a problem, it will be solved 4 times faster. That's perfect scaling. All right. So scaling suffers for extremely large problems. And that has to do with, again, for evaluating the FFT, you need information at all grid points. So if you break your domain up to different computers, they have to keep communicating with each other. So everybody knows everybody's data, right? Then one of the biggest ones is, Fourier transforms have trouble representing sharp discontinuities. Or shocks. Okay, and when I was, doing my PhD, one of my committee members said, no, Fourier transforms are awesome, they can do everything, right? But he forgot that when you have a sharp jump in U or in rho, Fourier transforms are terrible for being able to reconstruct that. Why do you think that is? If you remember, when we take the Fourier transform of a function, what is the assumption? That the function is, in terms of continuity, differentiability, and other things.
That is continuous?
Yeah, the function is continuous for sure, but think in terms of derivatives. So sharp discontinuities, what would the derivative be in space at these locations? Let's say the distribution of ink phi looks like a flat line and jumps flat line again. What's the derivative at the jump? What's the slope?
Very, very low.
Slope equals 0 is this, right?
Yeah. So close to infinity?
Yeah, the slope is basically infinity, right? And when we talk about Fourier transforms, we say the function that you take the Fourier transform of should be C infinity, or infinitely differentiable, right? So, so the issue that pops up is called Gibbs phenomena. Okay, and this just involves ringing at the discontinuity. Have you heard of this before? Okay, so this is a very important point, and just so you remember this, let me show you what it looks like. Okay, so let's see. Yeah, let me just run the. Okay, so what I've done is I've created this square wave, which is 0 here, jumps immediately to 2, then jumps down again to 0. Okay. And this portion is where we have an infinite jump. Not really infinite because I have discretized it, so there is, you can compute a finite value of the slope. But if it were a continuous function, this would be an infinite jump, right? So what happens, how many frequencies are in here? If you remember, we said any function can be represented as a sum of cosines and sines. How many wave numbers would I need to put in here? Can I do it with one sine, a few more sines? In case this is a little confusing, let me just put okay, so yeah, it's just the points. Right. So how many sine waves or cosine waves would you need to sum them up and reproduce this profile? Take a guess. On the order of 1,000, on the order of 10,000, a few hundred should be fine. 10 waves should be fine.
Is it the single? Is it just one condition, but all along the boundary points at x?
Wait, I don't understand. What do you mean? One condition?
Yeah, you're talking about the number of boundary conditions, periodic boundary conditions that are supposed to be used, isn't
no,
it?
No, no.
Isn't that?
I mean, if you break this up into Fourier coefficients, basically sine waves and cosine waves, how many different frequencies would you need to reconstruct this completely?
Yeah, so that's along the x direction.
Yes.
So it's just one condition, but the multiples of that, isn't it?
Wait, I'm confused. Okay, so let me go back, all right, and do create another. So let's see, y equals sine of let's say 5 times x plus 50 times sine of 10 times x. Okay, and if we visualize this now, let's see what it looks like. Wait. 50, 5, 10. Why does it look so nice? Oh, of course. Let's see. Aha, there. So, if I give you this signal and ask you how many sines and cosines do you need to break this up into, and then you can reproduce this completely, exactly. Does this question make sense? So the answer is 2, right? You just need 2 individual sines and cosines, one with sine 5x and the other with sine 10x. And the constant in front can be different, right? So it's the same question now. If I give you this strange looking function, how many sines and cosines can this be broken up into? So that when I recombine the sines and cosines, I will get exactly the same thing.
I mean, is it possible to, shouldn't it just be an infinite series, and shouldn't it be converging to an infinite series, and then the number of signs that we need is just an approximation of how accurate our prediction is?
Yeah, so you're actually going in the right direction. For reproducing a square wave, you need an infinite number of sines and cosines. So you need to have infinite number of Fourier coefficients for it, right? So, if, let's see, if it might be hard for you to believe that, so let's see, if we zoom in right now, everything is flat, right? But if we start taking the FFT, okay, let me comment that out and do this in real time. Let's say, okay, I have my y, let me convert it to the Fourier transform. So y hat equal FFT of y divided by n. N is length of y, all right? Okay. So if I visualize the Fourier coefficients, let's see, how do we do that? We do, I need a kappa vector. Kappa vector goes from 0 to n over 2 and minus e over 2 minus 1 to 1 to minus 1. Right? Okay. Kappa vector and the y hat. Right? Okay. So if I had my sine 5x and sine 10x, we would get two peaks. One at kappa equal 5, the other at kappa equal 10. Let's see what happens now. So if we do this, okay. See, now it's a very broadly spread out power spectrum. So we get peaks at close to kappa equal 0, but all of these high frequency wave numbers have some non-zero value. Okay? And this looks very useless, right? It's very small. After, let's say, 50, the energy content is too small. So we could potentially remove them. And let's see what happens when we remove them. So first, let's go back from y hat to reconstructed y. So let's see. You will say y reconstructed equal FFT, no, inverse FFT of y hat. Okay. And what will happen if we plot that? If we plot that, so exact answer is in red circles, and the reconstructed answer is in whatever color it comes out to. Okay, we plot that and we get an exact reconstruction. Right? We zoom in and everything is perfectly flat. Right? But let's see, if I remove one wave number, let's see. Let's see, 0 index equal 5, kappa vector greater than equal to 99. Okay, so I will remove one wave number and y hat of 0 index equals 0. So I'm setting it exactly to 0, even though it was small. And let's see. Okay. So everything looks good, except when we zoom in, you see the oscillations in the reconstructed function. And these oscillations will get worse. Remember we said, oh, everything beyond 50 looks useless. So let's see. If we kill everything beyond 50, what will it look like? Now it's very noticeable. That's not a good reconstruction. And this can be terrible if you think about the quantity you're trying to reconstruct is density. Zero density, one density, zero density. Makes sense? What is negative density? Physically, doesn't make sense. And this is density equal minus 0.1. So this is a huge issue when you deal with shocks using spectral methods. Okay. Does this make sense? So yeah, sharp discontinuities very difficult to represent with Fourier transforms. And you can see that very easily. If I remove more weight numbers, if I remove, let's say, 20, now you can really see. You don't even need to zoom in. Okay. So again, everything has an advantage and a disadvantage. Spectral methods are very nice. They are very high accuracy. They make our life easy by getting rid of the derivatives in space, but this is one big limitation. Discontinuities cannot be represented well. Okay. So to be able to simulate flows with discontinuities, people developed a very nice approach called finite volume methods. All right. So now we can actually start talking about those. Let me see if I missed something. All right. So that ringing is called Gibbs phenomenon. Okay. All right. So let's see. Volume methods. Okay. The main feature of finite volume methods is that we discretize the integral form of the conservation laws. Conservation laws being conservation of mass, momentum, and energy. And have you heard of finite volume methods before? They are basically what almost every commercial software uses. Okay. Most of them use finite volume methods. And again, there's several reasons for this. We can just write out some advantages. So the advantages are the finite volume method ensures exact conservation of mass and momentum even at very low grid resolutions. Okay. Another advantage is they are actually slightly easier to use with unstructured grids. Compared to finite difference. And by unstructured grids, I mean, if you have seen, actually you can take a look at what they look like. Let's see. Okay, so an unstructured mesh would be something that does not look like squares and rectangles anymore. It's mostly made up of triangles or hexahedrons or tetrahedrons. So there are many different kinds. There can be four-sided unstructured cells, three-sided cells. And finite volume methods are not very easy, but relatively more easy to implement than finite difference schemes. And why is that? So let's see, for instance, if we have a cylinder and we're trying to simulate flow over it, right? And we have a structured grid, what would we do with finite difference? With finite difference, we basically have del rho by del x, del rho by del t, plus u del rho by del x equals 0, right? Let's say this would be the d rho by dt equals 0 term. Okay. But if you have a nice body-fitted grid where you say, okay, no, this gives me too much uncertainty at the boundary cells. What I want to do instead is I want to create a mesh that has cells that fit the contour of the body. Okay, and here we had what? J equal 1, 2, 3, 4. We had I equal 1, 2, 3, 4. Now what we will have is eta equal 1, 2, 3, and C equal 1, 2, 3. Okay? So we basically use a mesh that matches our body shape. But if you think about it, we can no longer use d by dx or d by dy. You have to work in terms of d by dx and d by dx and d by d eta, right? So the differential equations have to be transformed to these grid coordinates, to these eta and c coordinates. And you can do that if you know how x, y are related to eta c as a function. You know, we just apply chain rule. And okay, fine, that works for this nice grid, it's feasible. But if you think about doing this with triangles on the surface, where each triangle looks different, it has a different size, different angles, this an insane amount of bookkeeping and transformation that you have to do now, right? I don't like making the unstructured meshes. Okay. So for each of these cells, the nice partial differential equation has to be transformed to account for what each individual cell looks like. Right? That's not feasible to do. So finite volume schemes are much better in that sense that they deal with mostly fluxes through the face of the cell. And we'll talk about that right now. So they are, compared to finite differences, they are slightly easier to use in the unstructured mesh case. Okay, let's see, did I miss something else? Okay, and right, so we also talked about finite volume schemes work well. when discontinuities might be present. And this happens mostly in hyperbolic systems, hyperbolic PDEs. So most compressible flow simulations are done with finite volume schemes. Okay. Again, with every advantage comes a disadvantage. So the disadvantage comes into how finite difference schemes are very simple to implement. We just divide our domain into points and evaluate the PDE. But with finite volume schemes, it becomes slightly more complicated. And we will see how that happens. Now, can you think about how exactly finite volume schemes are able to account for discontinuities? You know, if you think about differential equations, d by dx would become undefined when you have an infinite gradient. So how are finite volume schemes able to work around this issue? The answer was in the first line. We don't work with the differential form of the conservation laws anymore. We work with the integral. So most of the spatial derivatives disappear. Okay, and how does that happen? Let's see. Do you know how to derive the conservation laws, conservation of mass and conservation of momentum? We keep writing it over and over in class, but do you know where they come from? Oh. Oh.
These are laws.
They are laws given by whom? Why should we believe whoever said these are laws? We should not, right? So let's see. If we think about, let's take a one-dimensional example, all right? And let's divide it up into cells. Okay? So cells have a cell face and a cell center. And that's where the term finite volume comes from. So finite volume basically means divide up our domain into small control volumes. Which are basically the cells that we're talking about. And there's a cell face, there is a cell center. Okay, so working with the equations in 1D will be easier, but it might not make sense for you to think about a cell face in a one-dimensional line. So let me draw just one 3D control volume where we have okay, so if you think about a real problem, if you are simulating flow in this room, you divide the room up into small, let's say, cubic cells, or where now we have cell faces and we have cell center. Okay. And at the cell center, mostly we store, we use the cell centers to store scalar values, such as in fluid mechanics, what are the scalar values that we deal with in the momentum equation?
Density? Viscosity?
You could, but let's assume that it's not a wonky fluid. Viscosity is same everywhere.
Okay. Velocity?
Velocity is not scalar.
Yeah.
Mass.
Mass, yeah, density, where you integrate over volume, gives you the mass.
Location?
X, Y, Z, you will need both X, Y, Z of the center and of the faces. Right? So if you think about the momentum equation, we have rho, we have U, we have nu, and there's pressure. Pressure is a scalar. All right. And faces, we store vectors. Mostly we will store rho U together, and there's a reason for that. Rho U is a vector. Okay, so in 3D, the cells look like this. We will start working with the 1D case, just to keep things simple and just to make sure things become clear. Okay? And if we start numbering things here, we have I equal 1, 2, 3, 4. And the cell face, we can say this is xi minus half. This is xi plus half. And then the centers, we can say they are xi with I equal 1, 2, 3, 4. It's also sometimes you'll see the notation, this is called x east, x west, and that becomes very helpful when you deal with 2D or 3D things. So this would be x east, x west would be that face, x north, x south, x front, and x back. Okay, there's 6 faces. So you don't have to keep writing I plus half, j plus half, k plus half. All right, fine. So let's extract one of these cells and see what happens. So focusing on a single cell. Okay, so we have I, let's say we have rho stored here. And we know U. So remember, all the U's are stored at the faces and the rows are stored at the center. So we have U west and U east. And we have rho I. Okay? So if we start thinking about this single one-dimensional cell, what is the reason that the rho inside, the mass inside will change? How can I write down the mass? So let's look at rate of change of mass F. Inside the cell. Okay, so how can I write mass? What will mass I be?
Is the rho I VI?
Rho I, Vi,
Or,
correct? Yeah, rho dV. Right? And for the 1D case, it's, wait,
for what, sorry?
for the one-dimensional case we're looking at. You know, this is the general rho dV in this class, right?
Rho dx.
Yeah, rho x, dx. Limits?
I minus 1/2 to I plus 1/2.
Okay, fine. So rate of change of mass is basically time rate of change of x equals x. Let me write it as west to x east rho dx. Make sense? So this is rate of change of mass. Now, this is physically exact, the scenario we're looking at. Okay? We're thinking about the rate of change of mass, and this rate of change of mass will happen only because of what? In this picture we have shown here. Yeah. Does the question make sense? So we have everything we need on the picture. Rho, any quantity inside will change. Let's say, okay, rho is amount of ink inside the cell. The total ink content of the cell will change because what?
That's because of the velocity gradients.
Yeah, it's because of the velocity flux. Okay?
Flux.
The term is flux. It's because ink is being brought in by you, and it's being taken away by you. Okay? So the rate of change of mass inside the cell will be due to flux of mass into the cell minus flux out of the cell. Make sense? And all right, so what is the mathematical value of flux into the cell? Again, think of ink, all right? What is the rate of change of, what is the rate of ink being carried across the face? Rate of ink. You know what I mean.
U west times the west face.
You're saying it's U west times the area of the west face.
Yeah.
Yeah, that's correct. That gives you, but you multiply that with rho. Okay. So it's U west times rho west. And the outflow is there, right? U east times rho east. Okay? And you'll notice that there is a mismatch in the dimensions. Here we have, what do we have? We have 1 over second times kg over meter cubed times meter, right? And here we have meter per second, and here we have kg per meter cubed. Wait. So it works. Yeah. What? Did I miss something? Wait. B, the AT is 1, meter. Okay, I did not miss anything. And the reason for that is, okay, so again, with 1D, it always messes up my end. Let's do it in 2D cells. So if we have a 2D cell, what do we get? And when we do 2D simulations, we assume the length in the out of paper direction is 1, right? 1 unit. So this is delta y, this is delta x. And here flux would be, this is west and this is east. Flux would be rho west, u west times delta y. Okay? And the rho, the left hand side would be d by dt, rho d8, right? Rho dp, which into d becomes rho dx dy. So rho dx dy double integral. Yeah, so everything is consistent. Here we have kg over meter cubed. Here we have a meter squared. Here we have a 1 over second. And here we have the same kg over meter cubed. We have a meter over second, and we have a meter. And in 3D, you know, there would be a delta y times delta z. Z would be out of plane. Okay. All right. So here it's fine. Let's see. All right. Can we write this in terms of derivative? So what this is basically rho u at I minus half minus rho u at I plus half. Okay? And we know that if we were to evaluate the following integral, del by del x of rho u dx, this would give me the top line, right? Does this make sense? So us rho s is the same as rho u I minus half, and you know, I'm trying to change this to an integral form. So these two are exactly equivalent, right? And now I will write this one over here. There's a minus. There's a minus. Yeah, there's a minus. Okay, and then on the left hand side we have del I t xi minus half xi plus half rho dx. Okay. All right. Rate of change of rho in the cell is because of flux of the rho across the cell faces. Let me bring that to the other side, and what do we get? We get xi minus half xi plus half del by del t of rho plus del by del x of rho u whole thing dx equals 0. Does this look familiar?
The advection?
Advection. You are thinking about the advection equation will be a u d by dx rho. Okay. Which yeah, we can write it as so. We basically what we have is inside. We expand the term inside. We get rho u by dx plus u del rho by del x, right, equals 0. And this is the advection term. This is time rate of change. This is something. All right, and if we write this in general 3D, what do we get? We get del rho by del t plus u dot nabla rho plus rho nabla dot u equals 0. Okay, and this is what?
This is continue.
This is conservation of mass. Right? If you remember, incompressible means d rho by dt equals 0, which means this term equals 0, which by extension means nabla dot u equals 0. Okay, so the differential form of all the conservation laws are derived this way, based on logic. Okay? You take control volumes, you see what would be the cause of change of the quantity stored inside the cells. And when you collapse everything together, you recover the differential form. Make sense? Yeah, go ahead and ask.
My question is, what do we learn from this integral form? The reason that we derive that.
So the integral form is the basic form. Okay. The differential form is not the fundamental form. The conservation law comes from the integral form. Okay. And the reason we can work with the integral form instead is, well, let me show you. So why do we care? Why did we do this integral form at all? Okay.
Yes.
So, all right. Okay. Where did we start? We started. All right. So, how does the integral form and the fluxes and the flux help us in finite volume discretization? Okay, so I will rewrite one of the equations, this one. All right, so let me rewrite it. We had del by del t rho dx x west to x east equal rho west u west minus rho east u east. All right, and in 3D, this would be d by dt triple integral of rho dv equals rho. There are 6 terms, but let me just write out the x term. Rho west u west times. I don't know if you there's delta x, delta y, delta z. Okay, so let's forget about the 3D. Let's stick to 1D until things become clear. Okay, so fine. The right hand side, how can I write this? Let's see, if we think about a line integral, what does this represent?
Circulation.
Does it represent circulation? No, because there's a rho, right? UDL would be circulation. So the rho W, UW, rho E, UE, we can write as rho U dot N dl. Okay. Why? Because, okay, you tell me, why can we write this? It's relatively simple. So rho S, US minus rho E, rho S minus rho E. And the normal here points normal west points this way. So normal always points outside, away from the cell. Normal east points here. Okay. So this is negative. When we take u dot n, we get a negative. When we take u dot n east, we get a positive. Which is why we can write this as this, this as this. Okay. So this is just the flux form, all right? Okay, and again, we can jump from one form to another using the Gauss theorem, which this is just triple integral of nabla dot rho u dv. And let's go into the differential equation again. All right. So the main thing you should take away from this is we can jump from one form to the next very easily. And all the equations, conservation laws we have looked at either have a dV or a dA, and our goal is to go to this flux form. All right. So let's do it one by one. If we talk about again the conservation of mass, what can we say? We can say, okay, we have to describe one more thing. So let's say average density stored inside cell. How would I compute this? Let's say this is rho I bar. We can just say this is 1 over delta x integral of rho dx, x west to x east. Make sense? Okay. All right. And then again, this is the main equation. So let me rewrite that, which means del by del t of x west to x east rho dx is u west rho west minus u east rho east. Okay, and using this, I can replace this as del by del t delta x rho I at bar equal minus u west rho west minus u east rho east equal 0. Okay. What does this give me? This gives me rate of change of average rho inside the cell, and that is plus flux east minus flux west over delta x equals 0. Okay, where flux east is basically u east rho east. Does this make sense? So we have not done anything. We've just gone from the form of conservation law we know, which is in terms of derivatives, to the integral form, and then back to the fluxes. Okay? And the conservation law without any assumption becomes this. There's no assumption in here. Does this make sense? All right. So what do we do next? There's a d by dt here. What should we do? This is still, all on paper. How do we go to the computer?
Discretize.
Once more.
Discretize. What is it?
Okay, how should I do that?
So is rho I plus half I bar. What's between I plus half and this?
No, with finite volumes, what you do is you store the cell average values at the centers,
Okay.
not at the faces, all right? So we'll keep it at I.
Okay, times n plus 1 is rho I at n.
You're done. So this is what you have to solve for it to be a finite volume scheme. The fluxes are computed at the cell faces. The cell averages are computed at they're stored at the cell center. Okay? All right, let's see. Okay. Does this make sense? Why we jump from differential to integral to flux?
Yes. But my question is, why do we store the rho I in the we have just one rho I in a cell? Is that the definition of this method? Like in the beginning?
No, rho I, this is rho I bar, which means how much,
I see in the cell is average.
yeah, what is the average temperature of the room, right? You store it at one place. Rho I bar is not the same as the rho I, okay? Because next, my question to you will be, I don't really care about the average temperature. I want to know whether I should sit near that door or I should sit over here. I don't like the cold, right? So for that, you have to give me the distribution of rho. And there are several ways of doing this. You can say the rho in the whole cell, my assumption is it's equal to the average rho, which is a bad assumption. That's the simplest thing. You can go higher. What would you do next?
Adding different locations, different points. Or
No, instead of having a constant rho assumption throughout the room, what could you do?
distribution of the rho.
Like a linear
Linear
change in rho, right? You can say rho changes linearly from 20 degrees centigrade there to 30 over here. And the average is 15. That's what I would store at the center. So again, that's an assumption. That's something we don't know, right? And you can use a parabolic reconstruction for this. So there's different schemes that do this differently. And that's one big part of these finite volume schemes. How should you compute things at the cell faces that are not known? Because the rho is a very important quantity that you need to compute over and over. Go on. Oh, okay. All right. All right, okay, we will go on next time.